All right, let's talk about the math behind climate change. We're going to go step by step through exactly how you calculate and compare the impact of different greenhouse gases. And we're going to use a real-world example, methane. So if you've ever heard that term CO2 equivalent and wondered, what that really means, you are in the right place.
So here's what we're going to do. First, we'll quickly cover why a ton of one gas isn't the same as a ton of another. Then we'll get into the key metric that lets us compare them. That's global warming potential. After that, we'll set up our methane scenarios, we'll actually crunch the numbers, and you'll see exactly why this math is so incredibly important. Okay, let's dive right in. You hear the term carbon emissions thrown around all the time, right? But that's actually a bit of a simplification. The reality is, our atmosphere is dealing with a whole cocktail of different greenhouse gases, and each one packs a very different punch when it comes to warming the planet. And that brings us to the big question. What actually makes one gas worse than another? I mean, is a kilogram of methane really the same as a kilogram of CO2? Well, as we're about to find out, the answer is a huge no. So let's meet the main players. First, you've got carbon dioxide, CO2. It's the most famous one, mostly from burning fossil fuels. Then there's methane, CH4, which is the main ingredient in natural gas. And finally, nitrous oxide, N2O, which often comes from things like agriculture. And here's the key. Each one traps heat in its own unique way. So to compare all these different gases on a level playing field, scientists came up with what you could call a universal translator. It's called global warming potential, or GWP for short. And honestly, it's the most important concept for everything we're going to calculate today. Just think of GWP as a simple conversion factor. It takes all these different gases and translates their warming effect into one single unit that we can all understand, the CO2 equivalent, or CO2e. It's how we standardize the whole conversation about climate impact. Now, GWP is based on two really critical things. On the left, you've got radiative efficiency. That's basically how good a gas is at trapping heat. Think of it as its raw power. And on the right, you have atmospheric lifetime, which is exactly what it sounds like, how long the gas sticks around. Methane, for instance, is super potent, but it breaks down pretty fast. CO2, on the other hand, is less potent molecule for molecule, but it can hang around for centuries. GWP brilliantly accounts for both of those things. And here are the numbers we'll be using. These are the standard GWP values over 100-year period. By definition, CO2 is our baseline, our yardstick, so it gets a value of 1. Now look at methane. It comes in at 28. That means it's 28 times more powerful over that century. And nitrous oxide, a whopping 265 times more powerful. These are the magic numbers for our math. Let's just pause on that methane number for a second. 28 times. That means releasing 1 kilogram of methane into the atmosphere is like releasing 28 kilograms of CO2. It's a huge multiplier, and it's exactly why dealing with methane emissions is such a big deal. Okay, enough theory. Let's put this stuff to work on a real problem. We're going to take a sample of natural gas and analyze the emissions under a few different scenarios. This is where you can really see how the climate impact changes. We're going to look at 3 basic situations. The absolute worst case is venting. That's when unburned methane just goes straight into the air. A better option is flaring, where you at least burn the waste gas, turning the potent methane into less potent CO2. And the best case scenario is stationary combustion, where you burn that gas super efficiently to do something useful, like generate electricity. All right, time to roll up our sleeves and crunch some numbers. We're going to start with the absolute worst case scenario. What happens when we just vent that raw, unburned natural gas straight into the atmosphere? Okay, first things first, we need to figure out the actual mass of methane in 1 cubic meter of our gas. To do that, we use this formula. Don't let it scare you. We just take the fraction of methane in the gas, that's Y, multiply it by its molar mass, which is a constant, and then we divide by another constant, the molar volume of a gas. It's pretty straightforward. So let's plug in the numbers. Our gas is 80% methane, so that's 0.8. The molar mass of methane is about 16, and the molar volume is around 23.6. You run that calculation and boom, you find that every cubic meter of our gas holds just over half a kilogram of pure methane. Now for the magic trick. We take that mass of methane and translate it into its real climate impact. This is where that GWP number comes roaring back. We take the mass we just found and multiply it by methane's GWP, which is 28. We also add in the tiny bit of CO2 that was already in the gas, but really it's the methane that's doing all the heavy lifting here. And look at that result. It's pretty dramatic. That half a kilogram of methane, once you multiply it by its GWP of 28, has the same warming effect as over 15 kilograms of CO2. That just shows you the incredible power of that GWP multiplier. Venting is, without a doubt, a massive source of climate impact. So what happens if we don't just let the gas go? What happens if we actually burn it? Well, this is the whole idea behind mitigation. The goal is to chemically change that really high-impact methane, CH4, into much lower-impact carbon dioxide, CO2. Now, for flaring, the math gets a little more involved. Most of the methane turns into CO2, which is good, but a little bit, maybe 2% in this scenario, slips through unburned. We also create a tiny, tiny amount of nitrous oxide. So we've got to calculate the impact from all three of those gases and add them up. Okay, so we add up the CO2 equivalent from everything. The new CO2 we made, the 2% of methane that slipped by, and that little bit of N2O. And look at the total, it drops all the way down to just 1.8 kilograms of CO2 equivalent. That is a massive reduction from the 15 kilograms we saw with venting. Just huge. And what if we get even more efficient? Let's say we burn it at 99.5% efficiency, like in a power plant. Well, that means even less methane slips through. And that small improvement in efficiency drops the total climate impact even more, down to just under 1.6 kilograms of CO2e. Every little bit helps. So, we've done all this math. What's the big takeaway? Let's put our final numbers side by side so we can really see the difference between these scenarios in the real world. I mean, this picture says it all, doesn't it? Just look at that enormous bar for venting, way up there at over 15 kilos of CO2e. And then look at the tiny little bars for flaring and combustion. It's not even close. By simply burning the methane instead of releasing it, we have absolutely crushed its climate impact. Let's put one final number on it. If you shift from just venting this gas to burning it efficiently for a useful purpose, you reduce its total climate impact by nearly 90%. That right there is the power of understanding and applying this math. And that leaves us with one last really important question. The chemistry and the math here are crystal clear. Burning waste gas is way, way better for the climate than venting it. So the next logical question is, what are the real-world barriers, the economic, the regulatory, the engineering challenges that stop this from happening everywhere all the time? Well, that's a great topic for another day. Thanks for joining me.